what are linear transformations? These all important verbs in linear algebra. Well, the first thing we ought to know about them is that they're not particularly fancy. They're just functions, right? A linear transformation is a function whose domain is one vector space, let's call it V, and whose codomain is another vector space, W. So it takes vectors in V and it transforms them into vectors in W. That's all. Except that it also has to respect the structure that makes vector spaces. And that's what these two criteria above my head are doing. The two criteria tell me that a linear transformation has to send sums of vectors to sums of their images. In other words, if I add two vectors in my domain and then I transform them with my function, that I should get the same answer as if I transformed the two vectors first and then added their results in the codomain instead. So adding and then applying the function is the same thing as applying the function first and then adding. Right, so that's what property number 1 is telling me. Property number 2 is the same thing but for scalar multiplication. It tells me that if I take a vector in my domain and I scale it, multiply it by some scalar, and then I transform the result with my function, that I should get the same answer as if I first just transformed my original vector and then scaled its image by the same amount. Right? So scale and then transform is the same thing as transforming and then scaling. And that's all that we require for a function to be called a linear transformation, is it has to distribute over addition and it has to commute across scalar multiplication. So here's a picture of kind of how a linear transformation operates. What we're looking at here is two copies of two-dimensional space, R2, right? One on your left here is the domain of my function, and then the one on the right is my codomain. And so for every vector v that I select in my domain, it has an image vector t of v inside of the codomain. And so, at least for this linear transformation, different inputs appear to give me different outputs. And since a linear transformation is a function, every input is only going to have a single output over in the codomain. And so the linear transformation here is not this picture or that picture, it's the relationship between the picture on the left and the picture on the right. So that relationship is the linear transformation. And so this is one particular linear transformation. If we can transform all the vectors in two-dimensional space, it means we can also transform things like images, pictures that are sitting inside of that two-dimensional space. So I can take this cat face and move it somewhere, and that cat face can be transformed by my linear transformation also. By the way, what's something that we notice if I put this cat's eyeball right on the origin here? What do we notice about how this linear transformation is operating with respect to that cat's eye? One of the things we'll learn about linear transformations is that something that every linear transformation does is it leaves the origin in place, always. We can show that that follows from the definition of respecting addition and respecting scalar multiplication. So one of the things that we're going to see as we get toward the end of the course is that linear transformations also have a geometry. Right? If I take this square picture of a cat face and I use this linear transformation, it looks like it's giving me not a square, but some kind of parallelogram right over here. And we can do things like compare what's the area of the image parallelogram, the transformed cat face, versus the area of the original square. And if I change to different kinds of linear transformations, other kinds of stuff can happen too. Let's see if I can get a good example. Here's an interesting example. Here it doesn't look like my cat face is showing up over there in the codomain at all. And if I move my vector, my input vector, around a little bit, what do you notice about the output vectors from this particular linear transformation?
They're all on that single line?
They all look like they inhabit a single line. Whereas in our other examples, where we actually do get to see a cat face, right, my output vectors look like they're able to roam the entire xy plane. So that, according to our vocabulary, should be a difference in image. Right? The image of this linear transformation looks like it only consists of the points that are on that line that the t of v is exploring. So the image of this linear transformation is just going to be that diagonal line, because all the outputs are on that diagonal line. Whereas for my other examples, the images look like they can be anything inside of the xy plane. So when we get to talk about image and kernel, that's another part of what we'll be talking about. And geometrically speaking, it looks like linear transformations, in addition to sort of stretching, can also do some rotating. Like this cat face looks like it's rotated with respect to the original cat face. So a rotation of the xy plane would be an example of a linear transformation. We can also stretch. So I like cats, so if I wanted to stretch my cat out to be twice as much cat as before, then I could do a linear transformation, let's say like this one. Make this a 2, make this a 0. Ooh, wait, no, that didn't quite do it. I lost my image again. I think what I wanted was 0 here and 2 here. There we go. So now it looks like everything is the same except my cat is twice as large. Right? So I can stretch, I can make lengths bigger, I can make areas bigger. I don't have to stretch the same amount in the horizontal direction as I do the vertical. I could make a chunky cat that's 3 times wide and 2 times tall, right? So linear transformations seem like they can do a handful of different things geometrically, but they can't do just anything. So when we get into chapter G, our last chapter of the semester, we're going to figure out how to classify the geometry of linear transformations. If you give me a linear transformation defined by a matrix, for example, I should be able to tell you, is it stretching? Is it shrinking? Is it rotating? Is it, we saw this in the original example, but I didn't draw attention to it, so maybe I'll do that now. Here we go. Is it reflecting? So here's an example of a linear transformation that looks like it's reflecting this cat because this little spot on its chin looks like it's on the opposite side in the codomain as it was in the original. So linear transformations can stretch, they can shrink, they can reflect, they can rotate, they can project, which is what happens when we squished the image down into a line, and they can also shear, or what's called skew, which was the very first example we saw, where it looks like we just took the square image of the cat face and just sort of squished it over into a parallelogram instead. So this would be called a shearing transformation. The area actually remains the same for a shear, but the sort of the parallel sides don't make the same angles with the other parallel sides anymore. And it turns out that that's all. Those are the only 6 things that a linear transformation can do, and we'll see in chapter G why that's the case. So the linear transformation here is the relationship between the domain and the codomain. So coming back to the text, what is it that we can say about a linear transformation? Well, we can, first of all, given a function, we can determine whether it's a linear transformation just by checking that those characteristics are satisfied. That if I add first and then I apply my function, I get the same result as if I apply my function first and then add. So in this example here, we're given a function from 3-dimensional space into 2-dimensional space given by this formula, and then we can just verify that if I add xyz plus uvw and then transform the result, I get this quantity, which is the same as what I would get if I transformed xyz and uvw separately and then added the results of those 2 things together. And so since those are equal, it means that this function respects the addition operation. And we can also check that it respects the scalar multiplication operation at the end of the day. So that's, for this section, that's probably the most important thing to be able to do, is to verify that a given function is a linear transformation by checking these 2 properties. And of course, as usual, if we suspect that something is not a linear transformation, all we have to do is provide one counterexample, and that counterexample can and should be very specific as to why one or the other of those properties is not satisfied. So let's dig into an activity that I want to actually do this first one together.